Okay, so in this video, we are going to look at the topic of asymptotes. And as we will see, there are two types of asymptotes for a function, say y equals f of x. There are vertical asymptotes, and there are horizontal asymptotes. So let's look at the first type. We say that x equals a is a vertical asymptote of y equals f of x if either the limit of f of x as x approaches a from the left is positive or negative infinity, or the limit of f of x as a approaches a from the right is also plus or minus infinity. So simply put, a vertical asymptote of a function is a value of x where the function blows up either from the left or the right of this point. Let's look at a few examples. And as we will see, a function may have multiple vertical asymptotes. A function can have one vertical asymptote, 2, 3, 4, even an infinite number of vertical asymptotes. Let's take a simple example. So 1 over, say, x minus 1. Where could this function blow up? Well, we have a constant numerator. If we have a division by 0, the function would blow up. So if we let x approach 1, say from the right, and we look at the function 1 over x minus 1, we have a 1 over 0 case. Since x approaches 1 from the right, x is greater than 1, so x minus 1 will be positive. We have a 1 over positive 0 case, which gives us positive infinity. You can easily check that the limit of 1 over x minus 1 as x approaches 1 from the left gives you negative infinity. So if you were to sketch this function, you would get something that looks like this. The point x equals 1 is the point of interest. And we see that as we approach 1 from the right, the function blows up to infinity, so it will look something like this. And as we approach, as we've said, 1 from the left, this will approach negative infinity, so it will look something like this, around the point x equals 1. So that's our first example of a vertical asymptote. So here, x equals 1 is a vertical asymptote. Of the function y equals 1 over x minus 1. Let's look at an example where the function will have two vertical asymptotes. So let's say the function y is equal to x over x squared minus 4. We have a rational function, so again, a vertical asymptote is a point, a value of x, where the function blows up. Well, we have a ratio of two polynomials, both are defined, but since we have a division, we have to be wary of division by 0. And this will happen if x is either positive 2 or negative 2. Let's factor for a second x squared minus 4 as x minus 2 times x plus 2. And let's consider, say, the limit as x approaches 2 from the right. Of the function y, which is x over, and here we are going to factor as x minus 2 times x plus 2. We look at our case, x approaches 2, so the numerator approaches 2, over, well here, as x approaches 2, x plus 2 approaches 4. Now x minus 2 will be approaching 0, but the key is if x approaches 2 from the right, x is larger than 2, and so x minus 2 will be positive, so we will get a 2 over positive 0 case. which will give us positive infinity. So we see that as we approach 2 from the right, the function does blow up. So here, x equals 2 is a vertical asymptote. If we had approached 2 from the left, this would still be 2, this would still approach 4, but now x would be less than 2, and so x minus 2 would be negative, and we would be approaching negative infinity. Once again, concluding that x equals 2 is a vertical asymptote. Let's now look at x equals negative 2. And let's approach, say, from the left. Why not? The function again factored is x over x minus 2 times x plus 2. X will be approaching negative 2, so negative 2 on the numerator over. And once again, we will have a 0 coming from the negative 2 plus 2. The only question remaining is, will this be a positive or a negative 0? Well, let's see. You can draw the real line. The point of interest is negative 2. And because we approach negative 2 from the left, x is less than negative 2. So let's see. Now we know that this term here will approach negative 2, which is approaching negative 4. So this term right here is going to be negative. And now let's see, because x is less than negative 2, add 2 on both sides, and x plus 2 therefore is less than negative 2 plus 2, which is 0. So x plus 2 is also negative. But then we have a negative term times a negative term, which gives us a positive term. But because the numerator is negative, and here this is positive, the net result is negative, and 2 over 0 gives us an infinity, so we get negative infinity, which again confirms that the value x equals negative 2 is a vertical asymptote. So now you see this function has two distinct vertical asymptotes. Let's do 2 more examples. And then we'll consider the other type of asymptotes, namely horizontal asymptotes. So what if our function y is now, say, e to the x minus 1 minus x over, say, x squared? We have a quotient. Now the function e to the x is always defined. Same for 1, same for x. So the function on top is always defined, so it will never blow up. But we have, once again, a division, so we have to be wary about dividing by 0, which could possibly let the function go up to infinity and give us a vertical asymptote. So we have to check what happens around x equals 0. So let's figure out what is the limit. And here, again, x equals 0 is the only possible vertical asymptote. So we check. We have e to the x minus 1 minus x over x squared. Let's check for our case. We know that x squared goes to 0. E to the 0 is 1, minus 1 is 0, minus x, since x approaches 0, gives us that the numerator also is approaching 0. So we have an indeterminate case. So we don't know what's happening. And this is not an easy limit because we can't do anything really algebraically, but if you remember, we have a 0 over 0 case, so we can use here L'Hopital's rule. The limit stays the same, and if you remember, we now replace the numerator by its derivative. The derivative of e to the x is itself, e to the x, minus the derivative of 1, which is 0, minus the derivative of x, which is 1. This is now the new numerator, and we replace x squared by its derivative, which is simply 2x. We look at our case, As x goes to 0, so does 2x. E to the x approaches e to the 0, which is 1, minus 1 is also 0. So we have once again an indeterminate case, but because it's 0 over 0, we can use L'Hopital's rule one more time. We are still letting x approach 0. Replacing e to the x minus 1 by its derivative, which is e to the x. Replacing 2x by its derivative, which is 2. And now we are done, because as x goes to 0, e to the x will approach e to the 0, which is 1 over 2. Therefore, the limit is 1/2, which is clearly not positive or negative infinity. So you see that the only possible value of x that would possibly have given us a vertical asymptote was x equals 0. But the limit is finite. It's actually 1/2. So we get no vertical asymptote. So this function has no vertical asymptote. If you think of discontinuities, because if you plug in x equals 0 directly, you get 0 over 0. That is undefined. But as we let x approach 0, the function from both sides approaches 1/2. So the value x equals 0 actually was a removable discontinuity of this function. Let's look at an extreme example in the opposite direction. This function has no vertical asymptote. Let's consider an example where a function has an infinite number of vertical asymptotes. This will be our last example for vertical asymptotes. The function will be quite simple. 1 over, say, cos of x. Once again, both functions, 1 and cos of x, are defined everywhere. So individually, these functions don't cause us any problems. But we have once again a division, so we have to be wary of dividing by 0. And if we have a division by 0, this will, in this case, guarantee a vertical asymptote because the numerator is always 1. So we'll always get from the left or from the right of a 0 here, either positive or negative infinity, which will guarantee that we have found a vertical asymptote. So we're asking quite simply, when will cos of x be equal to 0? Well, if you think back to the unit circle, so the circle of radius 1 in the xy plane, if you draw a right triangle with hypotenuse 1, and the angle, say, here is x, cosine, if you remember, is the base of the triangle. So let's go from the angle being 0 and go counterclockwise. The base of our triangle will be 0 when we reach this point, because then we have a vertical line segment, so we have no width for our triangle, but this is 90 degrees, or if you prefer, pi over 2. If x equals pi over 2. But that's not the only value. We can also go up here, and we have again a vertical segment, so no width for the base of our triangle. This is pi over 2 plus pi, so it's 3 pi over 2. And we can keep going like this. Add, again, pi, you'll have cosine is 0, so 5 pi over 2. And we can keep going like this forever. 7 pi over 2. Because every time you add pi, you jump from one of these 2 points, which gives you a cosine value of 0. So you see that every single value will give you a 0 for cosine, therefore a vertical asymptote for the function y. But we could also go clockwise and start from 0 and go negative pi over 2, negative 3 pi over 2, and so forth. And these will all be zeros of cosine, therefore all vertical asymptotes of our function 1 over cosine. So all of these are vertical asymptotes of our function. We clearly have an infinite number of values, and so this function has an infinite number of vertical asymptotes. It's kind of a wild function. But that's really it. So when you look for vertical asymptotes, look for possible values of x where the function may blow up, and you will then verify that you have indeed found asymptotes that are vertical by considering the limit of the function around that point either from the left or from the right. Let's consider now the second type of asymptotes, and those are horizontal asymptotes. And vertical asymptotes were values of x. Horizontal asymptotes are values of y. So again, we have the function y equals f of x. So we say that y equals b is a horizontal asymptote of the function y equals f of x if either the limit as x goes to positive infinity of f of x equals b, or the limit as x goes to negative infinity of f of x approaches b. And if b satisfies this or this, b is called a horizontal asymptote of the function y equals f of x. In this case, we would say that b is a right horizontal asymptote because x approaches positive infinity. In this case, we would say that b is a left horizontal asymptote because x approaches negative infinity. Let's consider a few examples and see graphically what a horizontal asymptote represents. Quite simply, it says that as x either approaches positive or negative infinity, the y values of the graph will become closer and closer either from the right or from the left to the y value of b. One thing to mention, which is very important, is that if you look at the definition, either you will consider f of x as x approaches positive infinity, or you will consider f of x as x approaches negative infinity. Given a function f of x, these are the only two possible limits that may yield a value for a horizontal asymptote. Because we only ever have two limits, a function can never have more than two horizontal asymptotes. So here's our function. Let's take, say, x over, we'll go with the root of x squared plus 1. So we are asking when we look for a horizontal asymptote for the behavior of the function f of x as x goes to positive infinity, then as x goes to negative infinity. So we only have to find these two limits. And then we'll look at graphically how the horizontal asymptotes will fit into the graph of the function. So find our first limit as x goes to infinity of x over the root of x squared plus 1. Well, clearly here we have as x goes to infinity, an infinity over infinity case. Be very careful here not to apply L'Hopital's rule. If you remember, this was an example where if you apply L'Hopital's rule, it will actually loop in circles forever. Every time you have a ratio involving powers of x, and x either goes to positive or negative infinity, all you have to do is multiply top and bottom by 1 over the larger power of x. On top it is x, so we are going to multiply top and bottom by 1 over x. So 1 over x over 1 over x. This is simply 1. Let's multiply through. And here we'll also do something else here. Because x approaches positive infinity, x is positive. And so we can rewrite x as the root of x squared. But that's only because x is bigger than 0. This will give us, as x approaches positive infinity, well, x times 1 over x is simply 1. And here we're going to have root of x squared plus 1 divided by the root of x squared. We can use properties of the square root. The square root of a over root of b is the root of a over b. We can divide across here both terms by x squared. And we'll get 1 over the square root of x squared over x squared is 1 plus 1 over x squared. And now we have a very easy limit. As x goes to infinity, so does x squared. And so 1 over x squared will approach 0. And so we'll be left with 1 over the root of 1, which is root of 1 is 1. Therefore 1 over 1, which is simply 1. And so you see, as x approaches positive infinity, the function, the y values, are getting closer and closer to 1. So here we say that y equals 1 is a right horizontal asymptote. Let's now look for possibly a second horizontal asymptote, letting x approach now negative infinity. And if you look, it will be essentially the same work, except for one tiny detail. Oops, x approaches negative infinity. Now think of the solution. We'll just copy paste the solution. We'll have the only difference, this will be a negative infinity over infinity case. We'll still multiply top and bottom by 1 over x. The only difference here, because x approaches negative infinity, x is negative. And if x is negative, x is not the root of x squared, but x is then the negative of the root of x squared. So you'll have a negative here, which will be here, which will be here, so in the end you'll just get negative 1. And I will let you verify this. So you see that the y values of our function, as x approaches negative infinity, are getting closer and closer to negative 1. So we have a second horizontal asymptote, and because that was approaching negative infinity, this will be called a left horizontal asymptote. And let's just visualize roughly the graph of this function, keeping in mind that what we have now is a description of the behavior of the function for very large values of x. When x is really, really big and positive, the y values are really, really close to 1. And when x is really, really large and negative, the y values are really, really close to negative 1. So let's produce a very rough sketch of this function. So y equals 1 is a right horizontal asymptote. So let's draw a horizontal line where y equals 1. but only for the positive real values, because this is by letting x approach positive infinity. So here's our horizontal asymptote, our right horizontal asymptote, but the function also approaches -1 from the left as x approaches negative infinity. So here's the value y equals -1, and we will have our left horizontal asymptote. And now let's produce a very rough sketch of this function. When x is 0, you have 0 over the root of 1, which is 1, so you get 0 over 1, which is 0. And we don't really know what's happening here, but we know that when x becomes bigger and bigger and bigger, positively, the y values will become closer and closer to 1. So we know that, or at least we expect that the graph will look something like this. As x becomes bigger and bigger and bigger, the y values are getting closer and closer and closer to 1. And the larger x is, the closer the y value will be to 1. And as we now let x approach negative infinity, so x goes in this direction, the y values will be getting closer and closer and closer to -1. So we may expect something that looks like this. And the larger x is negatively, the closer y will be to -1. So we'll keep getting closer and closer to -1. So this is an example of a function with two distinct horizontal asymptote. Y equals 1 from the right, y equals -1 from the left. Let's look at just two more examples. And this will conclude our discussion of asymptotes, whether they be vertical or horizontal. Let's do a silly but still useful example, at least something to be aware of. A function may have no horizontal asymptote. Take a very simple function and y equals x cubed. The limit as x approaches, positive infinity of x cubed is simply positive infinity. So when x is bigger and bigger and bigger, the function blows up. So the y values are not getting closer to any single value. And as x goes to negative infinity, x cubed also goes to negative infinity. So you see that whether x approaches positive or negative infinity, the y values are not getting closer and closer to any fixed real number. So this function has no horizontal asymptote. And that's it. There's none. And here's our last example. Let's take y equals x times e to the x. So let's check for a possible right horizontal asymptote. The function is x times e to the x. Well, if you remember, we can graph x and e to the x. The graph of y equals x looks like this. The graph of e to the x, if you remember, is roughly 2.71828. So e to the 0 is 1. And as x becomes bigger, e to the x becomes bigger and bigger and bigger. So we have a very simple case. As x goes to infinity, clearly x goes to infinity, e to the x also goes to infinity. And so we have an infinity times infinity case. And here there is no ambiguity, the limit is infinite. So this function has no right horizontal asymptote. The limit blows up so it's not equal to a single real value. What about a possible left horizontal asymptote? Whoops. Ugh. Let me rewrite this. The limit as x approaches negative infinity of x times e to the x. Let's look at our case. As x goes to negative infinity, again, we're being redundant. X goes to negative infinity. But now look at the graph of e to the x. As x goes to negative infinity, e to the x will actually approach the x-axis, which means that the y values will be approaching 0. This is an indeterminate case, and it is a non-trivial case because one of the two factors is getting an absolute value bigger and bigger and bigger. The other is shrinking to 0. If you remember here, we can turn this into a L'Hopital's rule problem. If we send one of these terms to the denominator, and we'll send e to the x down, and let's see what we get. If we send e to the x to the denominator, it will become e to the negative x. Let's look at our case now. As x goes to negative infinity, we're being redundant. And as x goes to negative infinity, negative x goes to positive infinity. E to the infinity is just infinity. And this is great because we can now use L'Hopital's rule. We have an infinity or infinity case. The limit stays the same. Replacing x by its derivative, which is 1. The derivative of e to the negative x, by the chain rule, we get e to the negative x, coming from the derivative of the exponential function base e, times chain rule, the derivative of negative x, which is negative 1. But now what is our case? 1 is always 1 over, as we have said before, as x goes to negative infinity, e to the negative x approaches positive infinity. This goes to positive infinity times negative 1, so it approaches negative infinity. But if we divide 1 by something which is bigger and bigger and bigger, it will shrink to 0 from the negative side, but it still does shrink to 0. So you see that as x approaches negative infinity, the y values of our function are approaching 0. So y equals 0 is an asymptote, and it is a left horizontal asymptote. So you see that this function only has one asymptote that is horizontal, and that is a left horizontal asymptote. And this concludes our discussion of asymptotes. Recall the main difference between vertical and horizontal asymptote is a function may have any number of vertical asymptotes. It could have 0, 1, 2, 3, or an infinite number. But for the horizontal asymptotes, a function either has none, 1, or 2. And that's it.